Good morning, afternoon, or evening, everyone. My name is Aditya Parekh, and today I'll be presenting our research, real-time traffic camera data for enhanced route planning. This work was a collaborative effort between myself, Mariam Ahmed, Daniel Kachola, and Dehan Kwok, our mentor, at K University. Over the next 15 minutes, I'll take you through the challenges in our current navigation systems, our methodology for integrating real-time traffic data, and the results of our new innovative approach. Our focus is on bridging the gap between static navigation systems and dynamic user-centric tools by leveraging live traffic camera feeds and AI analysis. Urbanization has led to increasing challenges in managing traffic effectively. With a lot more vehicles on the road, unexpected traffic jams, road closure, and accidents are becoming more common, especially in metropolitan areas. While navigation apps like Google Maps or Waze or Apple Maps help identify the fastest routes, they often lack detailed visual information about current traffic conditions. For instance, you might get directed onto a highway only to find yourself stuck in bumper to bumper traffic. Our goal is to address this limitation by integrating live traffic camera feeds into navigation systems. These feeds will allow users to visually assess conditions in real time, enabling better decision making. By combining this data with computer vision techniques like vehicle detection, our system offers not just the fastest route, but also a smarter, more informed way to travel. Traffic congestion has far-reaching impacts on safety, efficiency, and even the environment. Current leading navigation tools rely on historical data and predictive algorithms, which often fail to capture the dynamic nature of urban traffic. This often leads to inefficient route recommendations during unexpected conditions, such as accidents or road closures. Our solution is to integrate live traffic camera data, enabling users to see current traffic conditions visually. This empowers them to make informed decisions and avoid areas with heavy congestion, ultimately improving their travel experience. Now, many researchers and developers have contributed to improving traffic navigation, and our work only builds upon these efforts. Hanchett et al. Introduced static camera systems for continuous visual traffic updates. This concept provided users with images of traffic, but it lacked integration with navigation tools. Ahmed et al. Took this further by developing interactive maps with public camera feeds, enabling users to explore global traffic visuals. However, this system didn't analyze the data, limiting its utility for real-time decision-making. Shazab et al. Applied YOLO models or other computer vision models to detect road conditions like potholes. This was a significant step towards using AI and computer vision for real-world traffic issues, but focused on road quality rather than congestion. Social vehicular navigation, or SVN, is another innovative approach. It uses vehicular clouds to create what they call Navi tweets, which are geotagged traffic snapshots. While this approach relies on community contributions, it highlights the potential of combining visual data and navigation tools. Finally, Google's bird's eye view navigation, which was recently launched, provides aerial perspective of routes. While visually helpful, it doesn't integrate real-time live traffic data or offer actionable insights. Our system builds upon all of these and is unique. It combines live camera feeds, real-time AI analysis, and route optimization all in a user-friendly package. This makes navigation a lot more dynamic and tailored to individual needs. This slide outlines the architecture of our system, which integrates several technologies to provide real-time traffic insights. This process begins with the user inputting their origin and destination into our system. The Google Maps API generates an initial route, which is originally represented as an encoded polyline. We then use the 511NY API to fetch live camera feeds from highways near the route. These feeds are analyzed using CV models, especially specifically Roboflow, which identifies vehicles and assesses congestion levels. Once the data is processed, we overlay it onto an interactive map. This map provides a visual representation of the route, with markers along it indicating camera locations and traffic conditions. The real strength of this architecture lies in its adaptability. It can be expanded to integrate additional data sources, like weather condition or road hazards, making it a versatile tool for both users and city planners. Not only that, but although it is only integrated with Google Maps, it can be integrated with any other API from other navigation systems such as Waze, Here Maps, Bing Maps, even Apple Maps. Our diagram, our system architecture diagram, illustrates how the various components interact to deliver a seamless user experience. Now you notice how each stage builds upon the previous one, which ensures accuracy and relevance in the data that we provide. So the first step in our system, like I said, is route planning. Using the Google Maps API, we generate a route represented as an encoded polyline. Polylines, if you're wondering, are strings of geographical coordinates that outline the route. These are decoded to map traffic camera data accurately to specific route segments. This forms the basis for integrating real-time traffic insights into the navigation process. The second step is integrating traffic cameras to provide real-time visual data. A spatial proximity algorithm first is used to identify cameras within a 10-meter radius, ensuring its relevance. To further refine the results, we have a calculate bearing function where we calculate the bearing of each camera and determine if that camera's orientation aligns with the user's travel direction. For example, an eastbound camera is only selected if the user is traveling east. This ensures users only see traffic information that is actionable and relevant, as if you're traveling north, you wouldn't care about viewing a camera that's facing south. To further analyze traffic conditions, we use Roboflow's object detection model, which is well suited for real-time applications. First, we collected a diverse dataset of around 930 images from live traffic feeds. These images covered a variety of conditions, including daytime, nighttime, and heavily congested traffic. To improve the model's performance, we applied image augmentation techniques. For example, we adjusted brightness levels, added reduced noise, and cropped images to simulate real-world challenges like poor visibility or camera artifacts. The training process was iterative. Each version of the model built upon the previous one, incorporating feedback and new data to enhance accuracy. This process was not only improved the model's ability to detect vehicles, but also ensured its robustness in varying conditions. For instance, the model can now handle nighttime scenarios with moderate accuracy, as you'll see later, and that is a significant improvement compared to earlier versions of it. This approach demonstrates how AI and computer vision can transform raw traffic images into actionable insights for navigation systems. Our vehicle detection model was evaluated using three metrics. The first one, precision. Precision measures the accuracy of vehicle detection, which is determined to be a high percentage of 88.8%. Recall, which measures the sensitivity to all vehicles, the model was able to achieve an 81.9% recall. Finally, the model was able to achieve a comprehensive performance metric of 89.5% for the mean average precision. These metrics reflect the system's ability to deliver reliable traffic insights under various conditions, as shown in this figure on the slide. Our model performed well across different conditions, like I mentioned before. Daytime detection was robust and accurate, as you can see in the first picture on the left. Nighttime detection improved significantly, but still faced some challenges in very low light scenarios, as you can see in the picture in the middle. Finally, dense or congested traffic conditions were also handled effectively with minimal errors, as you can see in the last picture on the right. Here's where it all comes together, the interactive map. When users select a route, the map displays markers at key locations where traffic cameras are available. These markers are clickable, allowing users to view live camera feeds. The feeds are enhanced with computer vision and AI analysis, showing vehicle counts, traffic density, and congestion levels. This real-time data empowers users to make better decisions, such as avoiding highly congested areas even if they are the shortest route. What sets this apart from existing navigation systems is the level of detail and interactivity. Users are not just passive recipients of route suggestions, but they also are able to actively engage with the data to make decisions that best suit their performance and needs. As you can see in this image, or in these images, the system provides a clear and intuitive interface. It makes it accessible not just for tech-savvy users, but also for the general public. Let's consider the broader impact of this system. For individual users, it reduces travel stress by providing real-time and actionable insights. For city planners, it offers a dynamic tool for managing managing traffic flow and addressing congestion in real time. And from an environmental perspective, you can avoid traffic jams that are significantly going to reduce fuel consumptions and emissions. Beyond these benefits, the system's adaptability is a key strength. By having the ability to integrate additional data sources like weather and road hazards, or additional navigation systems like Waze or Apple Maps, it can evolve into a comprehensive navigation solution. Ultimately, this research showcases how live traffic data, when combined with AI and computer vision, can transform navigation into a more dynamic and user-focused experience. To conclude, this research demonstrates how live traffic camera feeds can enhance route planning by providing real-time insights. Our system addresses the limitations of current navigation tools, offering a more user-focused experience. In the future, we would like to incorporate additional data sources like weather and road hazards, and also incorporate other APIs for other navigation systems, like I mentioned, Waze, Apple Maps, Here Maps, Bing Maps. And we want to enhance vehicle detection in these low light and adverse conditions. I'd like to thank my co-authors, Mariam Ahmed, Daniel Kachola, and our mentor, Dehan Kwok, for their collaboration and great help. A special thanks to Kane University for supporting this research and the organizations like the CSCI, the International Conference on Computational and Computational Science and Computational Intelligence, for providing resources for this work. I would also like to thank the National Science Foundation under grant 2318696 for the funding that I've received for this research. Thank you for your attention. If you have any questions, please email me at parekhad@kane.edu. That is PAREKH@KEN.edu. Thank you for your time.